Hello, everyone. Welcome back as we proceed with our lessons. And today we are going to look at measures of dispersion. We have been looking at measures of the center, and we'll see why it's very important that we look at measures of dispersion in conjunction with measures of the center. In most cases, we can also call these as measures of spread or variability. Where there is no variability, it's the same as there is no dispersion, but also there is no spread in a particular measure that we are looking at. We are basically going to look at three values that we need to consider in this lesson as measures of dispersion, or values that measure the amount of dispersion or variation in a particular set of observations that you have been given. And here we are going to look at the range. We are also going to look at the standard deviation. And finally, we are also going to look at the quartile deviation. So these three are the ones that we are going to consider in this lesson. Why is it important that we look at measures of spread or measures of variations or dispersion? In most cases, you want to choose the best brand. Let's say this is an example where you want to choose the best brand of medicine for your patients, and you are interested in how long the drug takes to cure a disease. The choices are narrowed to two different drugs. The results are shown in the chart. Now, for the chart, for that example, we want to see which drug would you choose. So here are two drugs, A and B, drug A and drug B. And the chart indicates the number of days a drug takes to cure a particular disease. So you have drug A. How long does drug A take to cure a particular disease? How long does drug B take to cure a particular disease? And let's say that you have recruited 6 individuals who are going to be assigned to drug A, and you have also recruited 6 individuals who are going to be assigned to take drug B. So for the first individual, it took 10 days for drug A to cure that particular disease. Another individual, it took 60 days to cure that particular disease. The third one, 50 days. The fourth one, 30 days. And the 40 days for the fifth, 20 days for the sixth. And for drug B, 35 days for the first, 45 the second, 30 days for the third, 35 days for the fourth, and 40 days for the fifth, 25 days for the sixth. What is interesting here, if you look at the total number of days it has taken for both drugs to cure a particular disease in these 6 patients in each drug is 210. And therefore, if you look at the total, you would not really make a difference as to which drug you would prefer to be the best drug to cure the disease in the shortest number of days, because what is so desirable for a drug is that it should be able to cure a particular disease in the shortest number of days. So in this case, you see that both of them are taking about, they are taking 210 days if you add for all the patients. But we can use the average. Does it help if we do that? For drug A, the average is equal to 210 days divided by 6 patients. So for each patient, it took on average 35 days to be cured. Now for drug B, it's the same story. You see that 210 divided by 6 is the same 35 days that it can take on average to cure a patient. So they both last 35 days to cure a disease. In this case, the average is not helpful at all to decide on to which drug one can buy to consider in terms of the number of days it can take to cure. They are both equally bad or equally good because the number of days is not different at all. So here, there is more that we can look into these observations. More information is required so that we can make such a decision as between these two drugs, which one is better than the other. Now, if we consider spread, in this case, we just take the maximum number of days it took for drug A to cure a patient, deduct the minimum. So maximum times minimum, which was 10 days, we see that the range is 50 days. So it can take as little as 10 days. Drug A can take as little as 10 days, but it can also take as way high as 60 days to cure a patient. Now, this could be due to differences in different patients, but if assuming that the patients that we recruited are from similar backgrounds, they have similar characteristics, so we really do not think that the patient characteristics would be very influential. Then we know that there is a lot of variation in the way this drug is acting. Drug B, if you look at the spread, it takes 20 days to heal an individual. So between the maximum number of days and the minimum number of days, you have a 20. Therefore, if you look at drug B, it has a smaller variability, which means that it performs more consistently. That means when somebody is taking a drug B, they're likely to have fewer number of days than when they are taking drug A. Because here now it means they spread, the way the days are spread between the lowest and the maximum, the spread is not too huge so that you can it's not as worrisome as in drug A, because in drug A, the likelihood that somebody can go up to 60 is also there. But in drug B, the chances that somebody can go beyond 45 days is a little bit narrow. So we have 20 days here. So if you were to make a choice based on just this, the range, then choosing drug B would be better. Whether you spend 45 days, it's still okay, because if you look at drug number A, then you see that you can even go up to 50 something days, you can go to 60 days. But for drug B, the maximum is 45, which is a little bit more desirable than the figures that we have in drug A. So you will realize that in the previous slide, basically we have used the range as the measure of variability. So the range, to define it, is the difference between the lowest value in the set of observations and the highest value in that set. So it's the lowest minus the highest rather minus the lowest. That gives you the range, and it's the starting point to give you a picture of how spread your observations are, and from there you can use other measures also to complement that, so that you get more informed. If, for example, we are given this data set where we have observations, 40, 30, 15, 200, 37, 24, and 99. The range is simply the maximum minus the minimum. The maximum is 100 here, and the minimum is 2. So the range is 98. And it carries the units as those in the individual observations. If this was in time, in minutes, it will still be in minutes. If this was in meters, it would be meters. If this was maybe in days, the range will still be in days. Now, we can move further to look at the deviation from the mean. So deviation from the mean is basically looking at distance. How far is each observation on average from their mean, from its mean? So a deviation from the mean, x minus x bar, is the difference between the value of x and the mean x bar. So we base our formulas for variance and standard deviation on the amount that they deviate from the mean. You might recall that we already looked at the maybe some of deviations about the mean, but also some of square deviations about the mean. So we said that some of deviations about the mean, first of all, you are looking at deviations themselves. And so here we are basically looking at deviations, which is the distance between the mean and each of the observations. So, but how we are going to deal with that, let's see in the next slide. So here we are going to look at the formulas for sample and population variances. If you look at the formula here, basically, it's so familiar to what we have seen before on sums of squares, or sums of square deviations from the mean, which was just every xi minus x bar square. Then you sum those squared deviations. And if you look at this formula, I think it should also be a familiar formula, that the top part here, which you see here. Now this we call the correction factor, and this one we call raw sums of squares. And this one is the sum of squares of sum of square deviations from the mean. So you see that the top part here is just the same as the top part there. Now what is not as familiar to you, it should be this one. So which is n minus 1, n minus 1. But I know you're familiar with n, you're familiar with n over there. You're familiar with the top, but maybe not everything like this. So if you look at, I'll start with this formula. Basically here you are taking sums of square deviations about the mean. You divide by n minus 1. So n basically is the sample size. So if you have a set of observations, if you have 10 observations, then you're talking of 10 minus 1. Now this formula is very much used when you have a sample, while this formula is very much used when you have a population. So here we are talking of a population variance. Now a population variance, we should know mu. Mu here is a population mean. So we are already given a population mean. When we are given a population mean, we do not calculate an average. We don't calculate an average. We just subtract it from each of the observations that you have been given in that set of in that population. And so you divide by the n as it is. Here, we normally would subtract with a sample mean, and that's an average that has been obtained from the set of observations that you have. Now, it is believed that when you have 10 observations and you have used those observations to calculate an average, you have lost some degree of freedom or to use that set of observations, because if we are calculating a variance, we are basically going to use the same set of observations. Therefore, we need to subtract a 1 to show that we have already used some the same observations to calculate the sample mean. So we have lost some degree of freedom to use this set of observations, and that's why you see that many formulas for the sample mean, they'll be subtracting a 1 here. But most of the formulas for the population, not for the sample mean, but for the sample variance, will be subtracting a 1 there. And most of the formulas for the population variance would not subtract a 1 below there from an n. However, if you will be doing your computations, I advise you just use any of these formulas. If the question says that a sample was drawn from maybe this kind of population, then when you are calculating, please use the sample variance to do that. If it's a bit silent, you can use the population variance. You won't be penalized by doing that. So provided you have shown your formula, that will be in order. So you can either use this formula or this one, or use that formula or that one. They will give you the same answer. So this is a population variance. Now, if you look at what we have here, when you compute and get your answer for the population variance, what you are going to get basically is that you're going to get in units square. So if it's a distance in kilometers, you're going to get kilometers, square kilometers, or square meters, or square seconds, square minutes, square hours. Now, that does not come out good when you are reporting, and therefore that's why, because we want to report in the same units as the observations themselves, the variance is rarely reported, but the standard deviation. So the standard deviation is the one that is reported instead of the variance. And the standard deviation is basically the square root of the variance. So you get an S, which is just the square root of the variance. And we know the formula for the variance. So if you are asked to calculate a standard deviation, then that is quite simple, because you just go and work on the variance, and then you just take the square root of that variance to get the standard deviation. Now, for the example that we have been given, you are not necessarily the one that we had, but for this example, find the variance of the following data sets. You have 6, 3, 8, 5, and 3 in hours. So what is the variance for this? Now, we can use any of the formulas. If we want to use the one with a correction, then we need to square 6, 36, 9, 64, 25, and 9. And here, we can now just, because we have now raw sums of squares, then we know that for summation of x squared, it's just 143. And the summation of x is also given here, 25. So what you are going to do, you just have to square 25 and divide by n. And then below there, we divide by n minus 1. Actually, if you look at this one, it was equally okay just to divide by n, because so far we have not calculated a mean, but the spirit of subtracting a 1 from n is that we have used this formula to calculate the mean already. So if you look here, it was just okay not to divide by n. But as I said, well, if you do that, the answers might not be that very different. So if we input the figures, 143 for this, 25 square for that, and 5 here and a 4 below there, we just simplify that and we get 4.5 hours. So for 4.5 hours, that's our variance for this data set. Now, if we want to find the standard deviation, then we just have to take the square root of 4.5. So in terms of the standard deviation, we have 2.1 hours. So this is the measure of spread of hours or in that data set. It depends with the phenomena that you are studying. You can regard this as a small variance or maybe as a large one. But the very key thing is that you desire to have small variances because that shows that your data is not very much widely spread. If it was a measuring instrument, that gives you, it generates observations, and from that set you have a very small variance, it would show that that measuring instrument is very precise. On the other hand, if you have a very wide or big variance, it shows that instrument is not consistent to give you similar values. It can generate any values. It's more or less like it's doing it at random. So it can give you a very big value. It can give you a very small value. It's not consistent, so it's not reliable. If you want to generate values, then you wouldn't use it, but look for an instrument that it has a small variability, small spread. You know this one is consistent. If it has to give me a value, that value is more likely to be true. So, so far, this is how you can use the standard deviation. That's how you can use the range, the standard deviation, and I will later take you through the quartile deviation, how that is also used, and in that vein, we also look at the whisker and box plots because they go together. For now, I should say thank you so much and goodbye.